Today we're going to be doing rates of reactions. Should not take long. This is like part 1 of rates of reactions. Tomorrow we're going to do part 2. It's pretty quick, pretty easy. So when we talk about rates of reactions, we're talking about the fact that reactions do have certain rates. So I could do a reaction and we could time it, and then I could say, okay, let's try and speed it up. And there's certain things that we could do to speed up the reaction from start to end, right? So, and then we could time it and it could be faster, or we could time it and we could make it slower, that kind of thing, all right? So what we want to do is first we want to talk about what is the properties that make a reaction rateable, like make a reaction timeable. So there is something called the collision theory. And the collision theory says there are basically 3 things that we're going to be looking at. Well, we're only going to be looking at 2 of them, but there are 3 things that matter in a reaction, all right? So 3 factors that play into the speed of a reaction. Bless you. Okay, number 1, and you may have remember this from biology, because there was a lot of talk about this in biology, is the orientation of the molecules. So the orientation of the molecules. So this is that the molecules have to be oriented in the proper situation. So for example, if the nitrogen of the ammonia needs to react with the hydrogen of the next molecule, then when they meet, the nitrogen and the hydrogen have to be facing each other. So if the nitrogen bangs into the other nitrogen, that's not going to work, right? They have to be positioned in the proper place in order for them to react with each other. So this is the orientation of the molecules, which is that the correct sides of the molecules must collide. And there's a lot of ways, so this is for example, because there's a lot of ways that this correct orientation, this orientation of molecules plays out, especially when you think that molecules can be gigantic. They can have a chain of carbons that is 100 carbons long. And so now when you think, oh, it's super long, you think, oh yeah, it really does need to be oriented correctly. Like if it bumps into the other one and it's not in the right place, then that makes a lot of sense, since it has to flip this 100 chain molecule all the way around. That makes sense. The second thing that we're going to talk about is the number of collisions. And this is simply that the more collisions there are, the more likely the reaction will go. So the more collisions there are, the greater the chance that the reaction will go. Okay, the third is the one that we're really going to focus on a little bit today, and then we're done, so it's not a long day, all right? Number 3, this is activation energy. Okay, now you might remember, because we've already talked about energy, activation energy a little bit. Activation energy is here. The A here. Remember, activation energy is the energy needed to kick the ball at the top of the stairs, tap it to get it going. All right, and you might just have to give it a little tap. Or in this case, this is just a little tap, right, for this reaction, which is exothermic. Or in the case of an endothermic reaction, the activation energy is greater. All right? So in an endothermic, so the reactivation energy could be great or it could be smaller. So it depends. But more or less activation energy, we're going to talk a little bit more about this tomorrow. More or less activation energy changes the likelihood of the reaction going. Now, let's talk for a minute about this, because you could, so let's say you work in a laboratory and you have 3 partners and the 4 of you are standing there looking at your data and you are on the verge of, I don't know, curing cancer. So it's kind of big, right? And you have this sequence of, let's say, 15 reactions. And at the end of the 15 reactions, your result is that you have a reaction that targets the tumor. Okay? The 15th reaction goes in and targets the tumor. The problem is the first reaction, the very first reaction of this chain, has a very high activation energy. You know, I'm not talking like, a billion. I'm just saying, like, it's got a high activation energy. And so what would be really great is if you could lower that activation energy so that reaction would be more likely to go. Because remember, a high activation energy takes a high energy to get that reaction going. But if you could lower that activation energy, then you could get that reaction to start the chain, right? So that would be really great. So that's kind of important, starting that reaction, because that reaction would start the chain. So one of the things that you can do is you can add a catalyst. So a catalyst, and we're going to talk more about this tomorrow, but for right now, a catalyst lowers the activation energy. That's its job. It doesn't do anything else. A catalyst lowers the activation. Does it speed up the reaction? Nope, that's not its job. What's its job? Lower the activation energy. That's its job. Does that speed up the reaction? Yes, that will speed up the reaction. Why? Because it lowers the activation energy. Does it speed up the rest of the reaction? Nope. The only thing that it's going to do, and we're going to talk more about this tomorrow, is it's going to lower the activation energy. That's what it will do. Nothing else. Does it speed up the reaction? Ultimately, yes. How does it do that? Lowers the activation energy. I can't stress that enough. Now, enzymes, which you learned about last year, enzymes are catalysts. Okay? They are catalysts. What they do is they are reaction-specific catalysts. So remember last year, you learned about the DNA and how there was an enzyme polymerase which went into the DNA and broke it up, right? So that it could be replicated. Do you remember that? Please say yes. Right? And it split it off so that it could be replicated. But this was an enzyme that went in and broke these bonds. So it broke the ladder, the bonds. And then then this part was being replicated here, and this part was being replicated here. Do you remember that? Hopefully, right? So you would get 2 strands of DNA, okay? This was an enzyme. I'm not going to worry about the name of it. The reason, and so what this did was it made this reaction possible by lowering the activation energy. There were other things that happened, but this is an enzyme, all right? It lowered the activation energy. So it was a catalyst. Enzymes are catalysts, all right? So enzymes are catalysts. The thing is, all enzymes are catalysts. All enzymes are catalysts. We're going to go over this again tomorrow. All enzymes are catalysts. But not all catalysts are enzymes. Why? What's the difference between an enzyme and a catalyst? So that's the question. Why are all enzyme catalysts, but not all enzymes, all catalysts are enzymes? The difference is that enzymes are very specific catalysts. So this enzyme does only this. This enzyme does only this. And so this enzyme is a catalyst because it has only one job. All enzymes have only one job. They do only one thing, and this is their job. So all enzymes lower the activation energy. But not all catalysts are enzymes. For example, heat is a catalyst. It will lower the activation energy. It will speed up a reaction. But it is not reaction specific. So therefore, it is not an enzyme. Because enzymes are all reaction specific. Catalysts are not. So that's the difference. Enzymes are reaction specific. Catalysts are not. They do the same thing. They do the same thing. They both lower the activation energy, but they don't. But catalysts are not reaction specific. All right? So tomorrow we're going to, in part 2 of rates of reaction, we're going to talk about how we can speed up or slow down a reaction. And that will complete this unit. All right? So I don't know how much of a review sheet I'm going to give you because it's kind of going to look just like the notes because there's not that much, right? I mean, there's a few. I can give you some specific heat problems, but there's not that much in terms of other information. But we'll see. All right? So that's it for today.